Welcome back, students. Our objectives for today: explain what is meant by solubility product constants and calculate their values. Calculate solubilities using solubility product constants and carry out calculations to predict whether precipitates will form when solutions are combined. Solubility product. A saturated solution contains the maximum amount of solute possible at a given temperature in equilibrium with an undissolved excess of the substance. A saturated solution is not necessarily a concentrated solution. The equilibrium principles developed in this chapter apply to all saturated solutions of sparingly soluble salts. The heterogeneous equilibrium system in a saturated solution of silver chloride containing an excess of the solid salt is represented by AgCl, breaking down to give us Ag and Cl, but also those ions recombining to form AgCl. The solubility product constant, Ksp, of a substance is the product of the molar concentrations of its ions in a saturated solution, each raised to the power that is the coefficient of that ion in the balanced chemical equation. So in other words, it's the same thing. Notice that we'll never put the reactants in because the reactant will always be a solid. The equation for the solubility equilibrium expression for the dissolution reaction of AgCl is Ksp equals AgCl. The equilibrium expression is written without including the solid species. The numerical value of Ksp can be determined from solubility data. For a saturated solution of calcium fluoride, the equilibrium equation is calcium fluoride, well, you can see it. The expression for the solubility product constant is, there it is, the solubility of calcium fluoride is, and there's two ises there, so we'll just pretend that one doesn't exist. 8.6 times 10 to the negative 3 that'd be grams per 100 grams of water at 25 degrees Celsius. It's always looked at per 100 grams of water. That's how we define our solubility. Expressed in moles per liter, this concentration becomes 1.1 times 10 to the negative 3 moles per liter. Determining Ksp for reactions at chemical equilibrium. Well, first we write out our balanced chemical equation. Remember, the solubility product is only for those salts that have low solubility. Soluble salts such as sodium chloride and ammonium nitrate do not have Ksp values, or you could say they have Ksp values. Make sure that the reaction is at equilibrium. Chemical equations should always be written so that the solid salt is the reactant and the ions are products. Write a solubility product expression. To write the expression, write the products of the ion concentrations. Concentrations of any solid or pure liquid that take part in the reaction are left out because they never change. Complete the solubility product expression. To complete the expression, raise each concentration to a power equal to the substance's coefficients in the balanced chemical equation. Remember that Ksp values do depend on temperature. So, calcium fluoride dissociates to yield twice as many fluoride ions as calcium ions. Therefore, we end up with this as our expression, and we can calculate the Ksp by plugging in the molar concentrations. Calculations of Ksp ordinarily should be limited to two significant figures. After all, there's a lot of experimental error. So there's just a few solubility product constants. You don't have to memorize any of them. It's just to give you some general idea of the relationships here. Notice that they are, for the most part, very small values. The more negative the value is, the less soluble it is. So here, copper 2 sulfide is much less soluble than calcium sulfate. The solubility product constant is an equilibrium constant representing the product of the molar concentrations of its ions in a saturated solution. It has only one value for a given solid at a given temperature. The solubility of a solid is an equilibrium position that represents the amount of the solid required to form a saturated solution with a specific amount of solvent. It has an infinite number of possible values at a given temperature and is dependent on other conditions, such as the presence of a common ion. So here we're looking at a sample problem. Calculate the solubility product constant Ksp for copper 1 chloride. Given that the solubility of this compound at 25 degrees Celsius is 1.08 times 10 to the negative 2 grams per 100 grams of water. Alright, well, the first thing we need to do is figure out what our molar concentrations are. And so this is the general expression for that. Grams of copper chloride over grams of water, 100 grams of water. We converted that to milliliters and to liters, and we converted our grams to moles of copper chloride. And so we looked at our balanced chemical equation. That'd be our KSP expression. And we know that since it's a 1-to-1 ratio here, whatever this is, that is as well. So we find out our solubility. Just go ahead and reveal the whole thing. We plugged in numbers for the above expression. We found out that the solubility is 1.09 times 10 to the negative 3 moles per liter. Since these are both the same, we can just square that number, multiply it by itself, and we get the KSP. Notice that there are no units for KSP, as there are no units for KEQ, KAs, KBs, or any other K functions. Calculating solubilities. The solubility product constant can be used to determine the solubility of a sparingly soluble salt. How many moles of barium carbonate can be dissolved in 1 liter of water, 25 degrees Celsius? Well, to do that, we write our balanced chemical equation, calcium carbonate, KSP of barium carbonate. So our KSP, it's a 1-to-1 ratio for the barium carbonate. We can look up the KSP value for it, and it is 5.1 times 10 to the negative 9. We know that those are both going to be equal to each other, which is going to be equal to x. We know that x squared is equal to 5.1 times 10 to the negative 9. And that means the solubility, the molar solubility of barium carbonate is 7.1 times 10 to the negative 5 moles per liter. So, here's another example. Calculate the solubility of silver bromide. Go ahead and pause and see if you can do this one. It's based on the last slide. I'll give you about to count down to 5. So hopefully you paused and you're now back to see the answer. Did you get it? Hope so. Let's move on. Precipitation calculations. The equilibrium condition does not require that the two ion concentrations be equal. Equilibrium will still be established so that the ion product does not exceed the value of KSP for the system. If the ion product is less than the value of KSP at a particular temperature, the solution is unsaturated. If the ion product is greater than the value of KSP, a solid will precipitate. Unequal quantities of barium chloride and sodium carbonate are dissolved in water and the solutions are mixed. If the ion product, barium carbonate, exceeds the KSP of the barium carbonate, a precipitate of barium carbonate forms. Precipitation continues until the ion concentrations decrease to the point at which barium ions times carbonate ion concentrations equals the KSP. The solubility product can be used to predict whether a precipitate forms when two solutions are mixed. So using that, go ahead and take a shot at this one. I'm going to count down to 5. Alright, hopefully you tried it. The more you actually try these, the better you will get at them. The more easily it will come to you. So we're wondering if a precipitate will form here. So the first thing we have to do is we set up a balanced chemical equation. We use our KSP. We find out how many moles of barium we have, moles of sulfate we have. We know the total volume of our solution. They've told us how much we have to work with there. So we find out our total volumes. So we know how many moles of barium and how many moles of sulfate we have. We can calculate the molarity. So that's how many moles per liter of barium we have and how many moles per liter of sulfate we have. And the ion product constant, we go ahead and plug that on in there. That's what we get for the ion product. We notice that that is greater than the KSP value. So that means, yeah, we're going to see some precipitation forming. Alright, limitations on the use of KSP. The solubility product principle can be very useful when applied to solutions of sparingly soluble substances. It cannot be applied very successfully to solutions of moderately soluble or very soluble substances. The positive and negative ions attract each other, and this attraction becomes appreciable when the ions are close together. Sometimes it is necessary to consider two equilibria simultaneously. Just sort of a brief highlight of our equilibrium calculations. If it's slightly soluble, we can use solubility product constant, KSP, and for reversible reactions, we can use the equilibrium constant, KEQ, and in reality, they're pretty much the same system. Well, that concludes this section. Please write down any questions you have. Some of this gets a little bit trickier, so you should have a few. And I look forward to seeing you in class soon. Bye.